So I'd first like to thank the organisers for giving me this opportunity to talk to you, but I particularly want to thank I haven't turned the microphone on, sorry. Okay, can you hear me now? Yeah, so I was just saying I wanted to thank the organisers for giving me this opportunity, but I want to particularly thank all of the audience for staying to the bitter end of the final session. And I know several people have had to rush off to catch trains and flights and everything, but thank you for staying for the end. So, what I'm going to tell you about today is mostly new and unpublished work. So the health warning is that a lot of the stuff I'm talking to you about today I've not talked about before, so we'll see how it goes. But hopefully it'll be interesting. I thought it would be interesting to present some new calculations. But you will see lots of things that are familiar in this talk, because there are lots of themes running through this whole week, and I've particularly enjoyed the talks so far we've had this week. And hopefully you'll see some connections between what I'm talking about and what other people have talked about. So first of all, I'd like to acknowledge people who've done the work. So the important people involved in what I'm going to talk about today are particularly Raphael Voiturier and Davide Maranduzzo, who was here earlier. The person who's done most of the calculations I'll be showing today is my PhD student, Carl Whitfield. So with no further ado, I will get on and tell you what I'm going to talk to you about. So I'm going to start with an introduction and a motivation about cell motility. And then I'm going to present to you an active pneumatic droplet model. And I'm going to compare that to various similar models. And I'm then going to discuss the results that we've got in terms of force moments. And I'll then briefly talk about an extension to 3 dimensions. And if I have time, I'll compare this to a previous model of ours, which was a cortical model. We'll see if I've got time for that or not. So I'm just going to show you a little film to start with. Oh, it is moving. It was a bit quick. Let me do it again. So this is a breast cancer cell in matrigel, which is a kind of artificial tissue. And you see it's moving. One of the surprising things about this cell is that it's pretty spherical, which is extremely nice for modelling. Although I have to say that the more I think about this system, the more I think its spherical shape is probably an artifact of the experiment being in matrigel. But that's the experiment, so that's one of the motivations for what I'm going to talk about. This is a still image from that same experiment. I should say that these experiments were done in Institut Curie in Philippe Chauvier's group. And so what you see labelled here is actin, and these breast cancer cells move in this tissue. This is a 3-dimensional movement in the sense that it's not on a substrate. You can think of this as swimming in the medium, in the viscoelastic medium, but it's not crawling on a substrate like some of the cell motility stories we've heard this week. I'm now going to show you 2 cartoons that you would have seen, well, apparently according to the last speaker who showed it 1 million times, so I think this must be 1,000,001 times. It's this picture. I think everybody who's talked about anything to do with the cytoskeleton has shown that picture. It's quite famous now. I don't think I really need to introduce to you the basic ingredients of cytoskeleton models, because you've heard it several times before this week. But what I'd just like to say is that in most of what I'm going to talk about, it's this contractility that's important. So it's an active contractile stress that's generated by myosin motors binding to actin filaments and walking along them in different directions and pulling the filaments, so causing a contractile stress in the network. So this is, if those of you who were forward-thinking enough to jump sessions to the liquid crystal session earlier in the week to listen to Davide Maranduzzo's work, he showed this film then, and I'm going to attempt to show it to you again if it works. Hello. Oh, sorry, let's try this again. Oh dear, it worked when I tried it before. What you should see, oops. Well, Now I'm stuck. No, it's not playing. Okay, what you should see is that there's these red lines here are the director field or the polarization, and what you should see is that you see these are all pointing the same way, horizontally to start with, and then as the simulation runs, these start pointing outwards in a splay, and then this droplet moves. So this is a three-dimensional simulation in lattice Boltzmann simulations, and what I'm going to talk to you about is an analytical theory of the same kind of system. So I'm going to describe the model. This is a model of an active droplet. So I'm going to initially present it all to you in a two-dimensional case. So you'll see pictures of circles and everything like that. And then at the end, I will show you some results from the three-dimensional case, show how the results extend to 3 dimensions. But for simplicity, I will spend most of the presentation on a two-dimensional case. So we have a two-dimensional active droplet. This is an active polar fluid. It has a polarization P and a velocity V. I should say in terms of the geometry, we have a sphere of radius r, and we keep that geometry fixed. That's for analytical symmetry, simplicity. I'll make some comments about the geometry later on and my dreams as to what I'd quite like to do with this. But for what we've done so far, we have a fixed geometry of a sphere of radius r. I've said it's an active polar fluid. We're taking the long time limit, so we're approximating the viscoelastic active gel model to a viscous fluid. So this is the long time limit, which is the limit that we think is important for cell motility in this situation. The other thing I'd like to point out is that we have polar order, and you'll see P in all the equations, but it's essentially nematic, and that's because we don't have any treadmilling or any self-advection in the model of the liquid crystal type rods. They're not moving along in the polarization direction, as has been the case in many of the models that we've seen this week. What we're doing in this model is simply looking at the contractile stress term, and therefore it's essentially the nematic and the polar are give essentially the same behavior. So we start with the standard distortion-free energy, which here I've expressed in terms of P, the polarization. And this image here is taken from, we did a very simple lattice Boltzmann simulation of a passive polar droplet, where we put it, so it's polar inside this circle, and along this green bit, along this boundary that we're calling the front of the cell, we've specified that it needs to be radial anchoring here, and this is the steady state polarization field you get with that. Now, the reason I'm showing you that, this is a circle, yeah.
With an indicator term.
Yes, sorry. So yeah. Sorry, I've written it there generally, but yeah, we take the two-dimensional version. We also take the one constant approximation. Sorry, should have said that.
We just want to make sure we know you know all this.
Yeah, it was just testing me. Yeah, okay. This is the full lattice Boltzmann simulations, basically adapted from Davida's and Mike Cate's code that you may or may not have heard earlier this week. So this is an active polar gel in a droplet. This is with the phase field model that we heard a little bit about earlier today as well. And this is the steady state situation. Now you'll see it's not a circle. This circle is deformed. Now in our analytical calculations we cannot yet deform the geometry, but in the simulations the geometry is as a result of the simulations. That's not imposed. And neither is the polarization field imposed. So this is the polarization field you see, and you see that again it's splayed. Now this splay polarization is an a natural display instability is a natural instability you see in active gels. I should say contractile active gels. Yes.
Is this the same as the first case where you had one side with radial boundary, the other side free?
No, the difference. Sorry, no, that's wrong. This one, the differences are this one is a far simpler simulation. It's fixed to be in a circle. There's no phase field equations in here. It's simply the polar fluid with anchoring here, and it's passive. So it's far simpler.
So
It's
just minimizing the energy.
yeah, but just simply minimizing the energy. All I'm doing here is motivating the next step, which is this, which is that we basically impose, in the analytical calculations, we impose a splayed polarization field. So we break the symmetry by hand and we impose this splayed polarization field to start with. And then what we calculate is the velocity field that you get from this in a circular or later spherical boundary problem. So the reason we started with this splayed field is due to the evidence that I've shown you before, that you tend to see splay in bulk active gels, you also contractile gels, and you see it in simulations. And if you impose certain anchoring conditions, even in a passive gel, you will get this. So we use what we call a splay parameter, CS, which is simply the radius of this circle divided by L, where L is the length scale of the splay. So L will be from the center here to the point where the splay becomes, where the polarization vector becomes perpendicular. So we will be varying this splay parameter, and so I'll show you results of the effect of splay by using the splay parameter. Okay, so the equations are basically the standard active gel equations that you've seen before. As I said before, we are in the fluid limit, so we don't have any we don't have any elastic terms in here. I think I've got things here. So this is the viscous stress. These are the distortion stress. So this is essentially the same as pneumatic, although polar, although it's written in terms of the polar vector. And then finally, we have the active stress. I'm writing this in the 2D case. So actomyosin is contractile, so our active stress is zeta here is negative. And we have a fixed polarization, so we basically take H as 0. We have incompressibility as normal. And then we're obviously also in the low Reynolds number limit because of the sizes of the cell. And so we have the normal force balance equation here. And then we wanted to do analytical calculations. So we didn't want to do complicated systems, so we then simplified it further, and basically by taking only up to second order in the splay, which is R over L. And so these are our main equations written in that approximation. So then the important things in this, and what makes it complicated and what makes it slightly new, is the boundary conditions. We have no fluid flow across the boundary. So our VR is 0 at R is capital R. We also have, we impose an effective viscous friction at the boundary, and we're going to vary this friction coefficient. So I'd just like to say that we're not actually modelling the external medium here. We're modelling the flow inside the droplet and a friction to the external medium. So there's different ways in which you can interpret this coefficient. If the external medium is a solid, then this is the determines the effective slip. If the external medium, on the other hand, is fluid with viscosity eta external, and we're assuming non-slip, then this friction coefficient is related to the viscosity of the external fluid. So I'm not specifying the type of the external fluid here. We're simply modelling what happens inside the droplet.
So no slip would be zeta goes to infinity?
Yes, yes. So this is the non-slip case, which turns out to be the simplest case, which is why I'm showing it to you first. So to remind you, this is the polarization field which we impose, and then this is the velocity field which we calculate analytically based on this. And also based on the power. In order to solve the equations analytically, we assume power series solutions, and then we pin down the terms of those terms according to the symmetries and the boundary conditions that we've got. So this is for a no-slip boundary condition. What I want you to notice is that we get two vortices here going in opposite directions. So you've got a vortex there and a vortex there. Yeah, so two vortices. So what about finite friction? So finite friction condition, we get four vortices. So we've got two at the front, which were just like the two that you saw previously in the no-slip case, and we have two smaller vortices at the back. Now, in the case where there's no splay, in the no splay limit, then we get four vortices that are all symmetric. But for finite splay and finite friction, we get four vortices that are asymmetric, where the two at this side are larger than the two at that side. You will, of course, notice that I've already been talking about this as the front and this at the back. That will be obvious when we talk about the movement that this is creating. So, just want to show you the results of varying this splay and the friction. So, what we have here is we have the size of the rear vortices. So that's the size of these two smaller vortices, plotted as a function of the effective friction coefficient, and these different curves are for different splay. So I'm going to show you the...
Sorry, how do you define the size of the vortex?
How do we define the size of the vortex?
Yeah.
We've got the velocity field,
Right.
and we just define it in terms of where the gradient of the velocity field is 0 here, I think.
So
So it's just an effective measure of the asymmetry effect.
right, I'm just wondering, I mean, is it the distance from that...
Sorry.
There's a lot of points in that picture, and I'm assuming that what you mean by the size of the vortex is the distance between two of them, and I'm wondering which two. I mean, so take that vortex. The one
Vortex, the one I'm pointing on. Yeah.
I could define its size to be the distance from that center to the boundary.
Yeah.
I could define the size to be the distance from that center to the 4-point cross directly below your red dot.
Okay.
There's a lot of things I could define it by.
Okay, yeah, you're right. I don't actually know how my PhD student defined that. I should ask him.
Okay.
Incidentally, we plotted this against other kinds of measures of the asymmetry as well, and we decided this one was the most logical. Okay, so to show you what these flows look like, this is the no splay limit, so this corresponds to this point here in this splay parameter being 0. And you see here we have four symmetric vortices, and in this case the droplet is stationary. Over here we have the large splay, large friction limit, so this is this point, and here we effectively have two vortices here. But you see there's actually tiny vortices at the back, and you only get strictly two vortices in the infinite friction limit. And then this one is for large splay and small friction, so we get four vortices that are asymmetric. And similarly, but not exactly the same, for small splay and large friction, we also get two larger vortices at the front and two smaller ones at the back. This is the pressure field that we calculate. The only thing I'd like to say about this is that it implies that there will be a deformation on the sphere or the circle. So we don't calculate any deformations. We are fixing the geometry. However, that's rather artificial because we would expect in a more realistic situation the shape to actually deform, which is what's seen in the simulations. So here is the deformations from the last Sportsman simulations. These are the simulations from Davide Maranzuzzo in Edinburgh. And so here you see that when you have a situation where there's no splay, you have a deformation such that it elongates in this direction. You have four vortices that are symmetric, and this doesn't move. Then this is the motile state, and here you see the splay here and a deformed geometry, and again here you get two vortices. Interestingly, in all the lattice-Boltzmann simulations that we've seen of motile droplets, this is moving in this direction, they always have two vortices, unlike our asymmetric vortices. So we're wondering whether that's to do with the deformation here. So now I want to talk about force moments. So we have, if we take the net, we have the net force around the boundary is 0, as it should be for low Reynolds number. We then look at the dipole, and so this, I mean, these are the equations, but maybe the picture here is the picture here is easier to understand. Taking the dipole moments, in the x direction, we have effectively a contractile dipole, and in the y direction, we have an extensile dipole. And what's rather nice about that is it implies this, so intuitively. What we'd quite like to do is calculate that, but we haven't done that, and we're thinking about how to do that. Then we take the quadrupole moments, and the quadrupole moments, we've combined the x moments sort of here and here into one arrow here, forwards, and then backwards at the top and the bottom. And it's the quadrupole that gives us the indication of the mechanism for motion. So so what I'm basically saying is that the dipole tells us something about the deformation, and the quadrupole tells us something about the motion. And so this just tells you the calculation of that. And I'd just like to finish by showing you the 3D. So this is basically slicing through the 3D version. These are analytical calculations, and hopefully you'll be able to get an idea of basically what we've got is the same kind of vortices, but in 3 dimensions. Gone too far. Okay, I don't have time to talk about that. That was just to say that in a previous model with just the cortex and slightly different dynamics, we get a flow from the front round the edge to the back, which you can sort of map onto this bulk flow that I've been talking about today. And that was the equations for that. And I'd like to conclude and ask for questions. I think I have 2 chairs.
I would like to start. In the case where you have no splay, how do you get motion?
Oh, you mean how do you get flow field at all?
Yeah.
Okay, so we've got when you've got no splay, you've still got contraction because this is effectively pneumatic. So you've got contraction in that direction. This sling is to attempt to stop me waving my arms around too much, but you get that. And then you also have a non-trivial coupling with the boundary, because we have basically we've got a circular boundary imposed on the polarization.
But then you have 2 solutions. But you should have 2 solutions then, right?
Forward and back.
Because you said basically it's mimetic order.
Yeah.
So the flow field could be either way.
You mean the arrows could go either way? Well, hang on, let me go back to the oops. Let's look at this. So it's symmetric, so you don't. Oh no, it's going to take me ages. Sorry. Well, let's just look at this. Although it's not symmetric, but in the no splay case, each of these will be symmetric. But what you're saying is that each of these arrows should be different ways. Is that what you're saying?
No.
I mean, it doesn't move anywhere. It's just internal flows, basically. But it all cancels itself out, so it doesn't move anywhere. You have to have splay in order for it to move, because otherwise you don't have any symmetry breaking, so you're not going to. The droplet's not going to move.
I mean, I think, like the other chair, you seem to be using a kind of pneumatic, like free energy term for a polar vector. I mean, is that physically motivated? You think that the non-active part is like a pneumatic, the microdune.
Actually, the most general energy you could write down for a polar order parameter takes the same form. There aren't any new terms that come from breaking the polar symmetry.
Yeah.
I mean, other than surface terms.
With surface term and coupling.
Right, but if you just want to write down, yeah, okay.
Yeah, so if you're interested just in the contractile stress, then it is the same. It becomes totally different if you've got some kind of self-propel particles in there along.
To have, but
Exactly. Which I'm not.
Turned that off.
Yeah, I've turned that off artificially. I'm not claiming that that's not in the cytoskeleton. Of course it is, but we wanted to focus just on the effect of the active stress in these calculations.
I mean, so in that sense, it doesn't matter.
In that sense, it doesn't matter whether I write P or N.
Yeah. Okay.
I didn't get what was happening on the boundary of your cell, and I mean, how were the boundary conditions, and how you did that, and how was that in the lattice-Boltzmann also?
In a lattice-Boltzmann or in the analytical calculations?
In both.
Okay, well, I've got a slide for the analytical. Sorry. There we go. Okay, so in the analytical calculations, we impose no radial flow at the boundary and an effective viscous friction. Okay? That's quite different from the lattice-Boltzmann simulations, I should say, because the lattice-Boltzmann simulations don't have a true sharp boundary in the way we do. Their boundary is defined by a phase model, so they have phi, and phi is there's a term in the free energy for phi, which says that phi is 1 inside and 0 outside, but at the boundary it goes from 1 to 0. So they have a kind of fuzzy boundary, whereas we've got a sharp, clear boundary. So in terms of the boundary, ours is more defined.
But there is a flow outside, right? I mean, you show something like looks like flow inside and outside.
Yes. So in the analytical calculations, we don't calculate the flow outside, just inside. In the lattice-Boltzmann simulations, we calculate both inside and outside.
Okay.
In the interest of time, I think let's thank Rhoda again.